Hello. In this video we're going to look at some applications of radians, and the three that we'll be looking at are arc length, sector area, and angular and linear speed. All right, let's get going. All right, first up is arc length, which we were exposed to whenever we introduced radians. S equals r theta, and this theta must be in radians. So let's find the arc length given the central angle and the radius, which are the only two things that we need. In this first problem, the angle that I'm given is already in radians. So the sector area is just the radius times that central angle, which is just 5 pi over 4. But let's go ahead and write this out as a decimal, because that's how we're used to seeing lengths. So 5 pi over 4, that's about 3.9 centimeters. All right, in the next example, here I'll put a little line, the angle that we're given is in degrees. So the very first thing I need to do is change that to radians. And the way I'm going to do that is just take 60 and multiply it by pi over 180, which is just pi over 3 radians. So now the arc length will just be 2 times pi over 3. And because the radius was given to us in inches, we're actually going to multiply this out and see that this is about 2.1 inches. All right, so that's arc length. S equals r theta. If you liked arc length, you are going to love sector area. If you have a theta in radians, you can use 1/2 r squared theta. And this is just a little bit different than how you've done it in the past. Usually you do it as a proportion of, this area to the whole area. But this is just a different way of looking at it. So let's convert this to radians. And to do that, I just multiply it by pi over 180, and I get that it's 7 pi over 8 radians. So now I plug in everything that I was given, and I get that the area is 63 pi over 16, or about 12.4 square centimeters. All right, and that's sector area. All right, the next thing that we're going to talk about, and the last thing, is angular and linear speed. So here's what we're used to. We're used to, if you have a car, its velocity is some distance over time, right? Well, for circles, we're still going to use this distance over time type of thinking. You see, the rate at which an object moves along the path is its linear speed. And linear speed is given by v equals s over t. And it's often useful to remember that s is just r theta, like we talked about earlier. And then on the other hand, the rate at which an object rotates about a fixed point, it's called its angular speed. And it's given by omega equals theta over t. So again, let's look at these. The linear speed is the s over time. This is a distance around the circle over time. And then omega is the change in the angle over time. So this it very closely relates to velocity is just some distance over time. So let's practice it. All right, a bike tire rotates at 140 revolutions per minute. Find the angular speed in revolutions per minute. So the first thing I want to think is how many radians is each revolution? Each time that this goes around, how many radians is it sweeping through? 2 pi, right? It's going around the entire circle each revolution. And so we're doing this in revolutions per minute, so it's sweeping through 2 pi radians, right, 140 times per minute. So we can say that the angular speed is 280 pi radians per minute, or that's about 879.6 radians per minute. And again, just to quickly go over this, each revolution covers 2 pi radians. That's happening 140 times per minute, so that's why we multiplied those two numbers. All right, so now the tire turns at a constant rate of 2.5 revolutions per second. This is a change. Find the linear speed in miles per hour. So let's look at this. V equals s over t. So what's s? What's the arc length of each revolution? Well, remember that arc length is just the radius times the theta. All right, so let's figure out what r theta would be in this case. Well, r is just the radius. That's 15. But theta, I'm going to come over here and think about it. it's sweeping through how many radians every second? Well, each rotation, just like last time, each rotation is 2 pi radians, and it's happening 2.5 times every second. So theta in this case would be 5 pi. So I'm going to plug that in for theta. And this is happening every 1 second. So what this has given me is that V is equal to 75 pi, and this is in inches, since the radius was in inches, every 1 second. So its linear speed is 75 pi inches per second, but I need to know it in miles per hour. And to do that, I'm going to have to use dimensional analysis. Now, in this video, I'm not going to show exactly how dimensional analysis works. I'm just going to use it. The first thing I'm going to take care of is changing seconds to hours. You can see here how the units cancel each other. There are 60 seconds in a minute, and then there are 60 minutes in an hour. I've got my unit down to hours. Now I need to get inches into miles. So here I'll say, okay, there are 12 inches in 1 foot, and there are 5,280 feet in 1 mile. So here the units are going to cancel again, the inches, cancel the inches, feet, cancel feet, and my only units left are miles per hour. So I'm going to multiply across the top and divide by the bottom, and I get that the linear speed is about 13.4 miles per hour. All right, so we did arc length, sector area, and linear and angular speed. Goodbye.